All right, what's up, everybody? It's been a long time since I did some dynamics, so by special request, I've had some requests to do some, at least talk a little bit about pulley problems. So here, uh, I'm going to talk about absolute dependent motion, which for all intents and purposes are pulley problems here. And uh, um, and the thing that we're going to do here is we'll just define what dependent motion is and describe an approach to solve these pulley problems. I'll give you a general overview on how to do that, and then probably in another video or something I'll do some example problems. But really, dependent motion, as you could imagine, is motion of one particle that depends on another. So basically, one particle connected to another, and you can imagine all kinds of like pulley systems maybe where you have like a mass here and then another pulley on the ground over here and a mass over here. Bam, there's a pulley system right here. This has like a mass A and a mass B, or you could think of more complicated things, whatever they are, right? But that's a pulley system. Cranes are probably they have dependent motion as well. Elevators, depending on how they were built, and even gosh, what else? Just I guess just anything that's connected, right, with a cord, and you can model it, if you will, as two particles. So let's talk now. I guess I give you enough overview. Let's talk a little bit about what a pulley problem or how to solve these things right here. So let's see. My approach, and that that you can read in a lot of textbooks. I like Hibbler, but there's like Beer and Johnston and Miriam and Craig and stuff for dynamics. Those are probably the three most popular. But anyway, the general approach, like in any textbook, is you have a pulley system here. Uh, this drawing was inspired by Hibbler, so I'm not saying it's mine, but it's just I used Hibbler to inspire myself. But here I've got this mass at A, mass at B here connected by this cable, and really what you want to do is is for each particle, the first thing you want to do is select a reference or a datum for each particle. And that's important, the each particle. And so here, so for particle A, a characteristic of a reference or datum location is it has to be fixed, and you have to be able to, at least what's given, you have to be able to find the distances. So a fixed location for me, for A, this might be so 90 degrees to the direction of motion. So let's see, the datum should be fixed, and the line, it should be perpendicular to the motion of the particle. Motion of particle. So this is kind of like our characteristics of the datum here. So for A, I would choose here, this would be my reference or datum, datum for A. And then for B, I would choose 90 degrees to this, and that would be right about like that right here. So date A, datum for A, for particle A, and datum for particle B. And I can't tell you enough that this is probably the most important thing, is defining this datum and then saying what is positive with respect to the reference. And so I'm going to say motion this way is considered positive, or direction this way is my positive orientation or my positive distance. That's very important. What is positive? That way, when A is moving towards the datum, or if it moves towards the datum, then that's considered negative motion, okay, versus B moving towards the datum. So if I'm moving away from the datum in this case, that's considered positive motion. And now I have this. The next thing I want to do is to find the distances from the datum to the particle, or to the first part of the particle. So here in this case, right here, particle A is really this little fixed pulley here to accommodate the cable, um, and then the mass of A here. So really the distance for A here is, I can choose probably, maybe I would choose right here. And I would say the distance from the datum to here, right here, to define this distance is, I'll call this plus SA. Okay, so that's the distance from here to there, right here. Or I could, you could argue that distance is really to that first location right here where that little pulley dot is there. Because, when A moves that much, or that speed, that point right here on the pulley wheel also moves at that same speed, because they're all connected. That's one big particle, if you will. All right. So this is SA here. And then for B, the distance from B right here, bam, to right here, the distance, the position of B from the particle, from the reference right here is that distance there. Okay, and these distances are going to be really important for us when we develop an equation right here for the length of the cable, right? And so here in this case right here, when we want to develop a length for this cable, an equation for the length of this cable, it's just saying I broke this cable up into parts, and I want to sum them up using how I define these parts. Okay, so to do that, the blue line is the cable in this case. I would have for the cable, so let me use blue, cable length. Cable length is equal to, let's see, I have one of these SB lengths, so the distance from the datum to here, this portion right here to here is a length SB, plus I have a distance from here to here. And I have two of these distances. So that would be plus 2SA. And if I want to be nitpicky, I've got really this little portion right here. So I'll call that, shoot, what should I call that? I'll call that uh, L1, and then I've got even this portion around the pulley, and I'll call that L2, and those plus L1 plus L2, and those lengths right here, L1 and L2, are constant. They're also constant. And so this cable length, assuming it doesn't stretch, which is true, right? We're going to assume cable does not stretch right here. And so here, if I take a time derivative, which is next right here, if I take the time derivatives right here, bye-bye. If I take the time derivatives, sorry for the red line, if I take these time derivatives here of this equation right here, if I take a time derivative of this cable length equation, let's see, the cable length is constant, so the time derivative of that would be 0. That would be dsb dt plus 2 dsa dt plus the L1 length here, no matter where I am, is going to be 0. Or I'm sorry, the derivative will be time derivative will be 0 because L1 is always remains constant, as does L2. So essentially plus 0. This is the same as saying 0 is equal to the velocity of B plus the velocity of A. Okay, which means that VB is equal to minus VA. And that makes sense. It means that if VA is moving away, right here, in a positive direction, away from the datum, then B is going to be negative, right? The velocity will be negative, or it's going to be moving towards the datum, which is we define as negative. And what's more, if I take a second derivative, second time derivative, so if I take another derivative of this velocity, you know that it becomes acceleration. And so that would tell me AB plus 2. Oh, snap. I almost messed this up. This should be 2VA right here, and this should be minus 2VA, like that right here. 2AA is equal to 0, AB plus 2A, and so my acceleration relationship between these two particles is that AB is equal to minus 2AA, right? And then that just says about the acceleration, okay? So let's see here. I think that's good. And then once you have these, usually these end up being either the velocity or the acceleration relationship. It ends up being the one other equation you need to solve a kinematic problem. And so we'll do an example of that in a second. All right. See you soon. Hope you enjoyed it. Bye.